Okay, thank you everyone for attending this session. Today is one of the sessions that we have a lot of participants. We really appreciate your support. And welcome to Spring 2021 seminar series. Today we are hosting Dr. Gregory Mocko from Clemson University. This is graduate students community leadership team academic for this academic year. Roshan and Rodney are the coaches. Rajmohan, Tarun, Rachel, and I are taking care of the publicity. Anirban and Emmanuel are the support team. And Robert and Farooq are taking care of the correspondence communications. We have regular meetings Fridays at 4. You are very welcome to join us. If you want to join us, we can accommodate you, and you can send an email to Rodney and Roshan for the invitation. And we are a student organization, and we really appreciate if you become a member. If you can just take a photo of this image, you can become a member in the Engage, then we can get the support from the university to operate. So I just wait a couple of seconds here, and I will share the slides in the chat box, so you can become a member by going through this link as well. And we have a Facebook page that we update, we post our events. You will find the seminar series with advertisements and other social events that we have here. And also we started a YouTube channel for graduate students community. During the pandemic, we recorded all our seminars, and we hope that we can continue this tradition, so you can listen to the most outstanding people in these fields whenever you want. And we have upcoming events, a social event, the Fiddle and Fiddling. Rachel will be hosting that. And laser scanning microscopy in material engineering. Dr. Gu will be hosting that, will be giving that talk. And today we are having Dr. Mocko. He is an associate professor in the Department of Mechanical Engineering at Clemson University. He is the Associate Director of Education and Training at the Product Life Cycle Management Center, and he's the Educational Director of the Advanced Manufacturing track at Clemson University. His research interests include distributed design and manufacturing of complex systems, Industry 4.0, and knowledge capture in manufacturing and modeling and simulation. His research is supported by NSF, BMW Manufacturing Corporation, BMW AG, National Institute of Standards and Technology, Johnson Controls, and US Army, the Boeing Company, South Carolina Department of Commerce, and Fraunhofer USA Alliance. He served as the Mechanical Engineering Department Capstone Program Coordinator for over 10 years, working with industry partners and students to address design and manufacturing challenges. Also, he has led multi-university student projects focused on distributed design and manufacturing of UAVs and sustainable manufacturing. So we are very happy to have Dr. Mocko today. With that, Dr. Mocko, the floor is yours.
Okay, so let's see if I can share my screen.
Yeah, I stopped sharing.
So I think I can everybody see my slides okay, or
Yes.
see if this works? Awesome. So I did not have a cat problem until the beginning of the pandemic, so about a year ago, and then we got a cat, and I never thought I was a cat person. It turns out this rescue cat has grown on me a bit. So you're not unique in this situation, Rachel. I'm hoping that I can keep him at bay here for a little bit. Well, thank you for the invitation. I'm delighted to be here, and it was great to get introduced to everybody. Give you a little bit of background about me, and I'll spend a little bit about Clemson, some bigger efforts here at Clemson, and then I'll go into sort of a current research project that we are working on. So for those of you who don't know where Clemson is, I've sort of taken just a little snapshot here. We're in the very upper northwestern corner of South Carolina, about 2 hours from Atlanta and 2 hours from Charlotte. It's a wonderful place to be. It's a great place to be in terms of our capstone students, as Clemson and the surrounding area has got a wealth of companies ranging from Boeing, which has had an unfortunate fortunate run the last year or so, BMW, and a number of automobile suppliers, really within a stone's throw of the university. So that's been a real pleasure. This is a picture of campus. So I think about 4 years ago, I visited University of Oklahoma, and similar to you, we have our stadium on campus, which is certainly makes for a buzz around game day. What you'll see there in the horizon is basically looking northwest is sort of the Blue Ridge Mountains. There is a very large man-made lake there by the Army Corps of Engineers. So the university actually has a beach. And surprisingly, this week the campus probably looks like this. We're hitting the 70-degree marks this week. So aside from a few puddles and some mud, campus actually will be looking like this. So a little bit of an overview. I'm not going to go through all of these numbers, but we've got about 18,000 undergraduate students and about 5,000 graduate students, with the intent to grow over the next 10 years. We've got about 1,000 undergraduate engineering students in mechanical. We are the largest department on campus, and that's sophomore through senior. So at Clemson, all freshmen go through a general engineering program. Something that is good for our students is a number of our undergraduate students go to co-op or internships. So there's a really great cooperative education program. And then since I've been at Clemson, not because of me, but since I've been here, our graduate program has grown quite a bit. And these are the current numbers here in terms of faculty. I think we may have hired a couple here. So just because I was doing it, that's me in 2017 when I visited. I think that was the picture I sent. That's me in 2021. I have to say I don't look terribly different in those 4 years, so I don't know if that's a good thing or bad thing. But it is what it is. Teaching wise, I'll sort of expound on this. You can read this, but for the last 7 years, I have both participated and led an effort in a multi-university capstone program, specifically focused on the design of small unmanned aerial vehicles. It should be noted that I'm not interested in UAVs, or I wasn't interested in UAVs. I was really interested in the challenge of how does a group of students distributed across the United States actually come together and design, test, manufacture, and ultimately fly a 12-pound unmanned aerial vehicle. And so this year, last year there were 11 universities or 11 institutions involved, 10 four-year undergraduate institutions and one community college. And there was about 90 students involved in that. This year, due to COVID, there are 4 universities involved and 40 students. These are universities distributed across the United States: Iowa State, Brigham Young, Clemson, and Purdue. And what we do is we put approximately 10 students on each team. So they're not competing against each other, or universities are not competing against each other, but about 10 students on each team. And those students are responsible for realizing a system, and not paper-based system, but an actual physical system. Parts are manufactured in different locations. Tolerances are often overlooked, so parts don't necessarily fit together as though they would anticipate within CAD. Students are doing anywhere from carbon fiber layup to 3D printing to programming autopilots, and this year what we'll have is 4 separate fly-offs. And so what's been interesting, again, pre-pandemic versus pandemic, the students in this class were really well suited to operate online, whether it be with certain technology, but often just accustomed to how do you communicate when you're not in the same room, in the same location, when you can't sort of walk down the hallway and speak amongst your team members. So that's been a really great experience for our students. We're learning some things. We are scoping research around it, and that could be with engagement, could be on tools. So there's been some really good advances in sort of collaborative CAD and manufacturing. So that's a bit about me. What I want to talk about today, and it's sort of shifting gears, is a larger effort at Clemson that I am part of, and this is the Virtual Prototyping of Ground Vehicles System Center. So what's known as VIPER, and actually this was rolled out about 10 months ago. What VIPER is looking at is next generation ground vehicles. Right now, if you look at the Army, if we look at the Ground Vehicle System Center, and we look at associated labs, we're sort of pre-autonomous vehicles. What they've been doing is kitting vehicles, existing vehicle platforms, and they've been putting kits on them to achieve some degree of autonomy. And what the Army is doing now is saying, what does a next generation of autonomous fleets of vehicles look like? They could be homogeneous fleets of vehicles. They could be inhomogeneous fleets of vehicles. They could be a mix of both ground vehicles as well as air support vehicles, but really looking about what that would look like. We are looking at predominantly 3 areas, and I'll touch on those 3 areas just to show you sort of the breadth of research that we're looking at. And I'm not in all 3 areas. First area is being autonomy, and so there's a number of researchers in this area that are looking at things like sensors and hardware, algorithms around the use of those sensors, sensor fusion, as well as sensor security. The researchers in this area range from faculty in automotive engineering to psychology to computer science and electrical engineering as well. So this is really looking at sort of the sensor and autonomous algorithms perspective. The second focus is looking at propulsion systems, energy storage, batteries, and thermal management of those systems. So a number of folks here are looking at how, what's the density of different battery chemistries? How do we manage thermal problems within that? What's the best powertrain to go with in terms of hybrid technologies? And how do we ultimately get that power from a power plant to the ground? And then some innovative things about sort of decentralized sort of energy sharing amongst vehicles. And again, faculty in this area range from ECE faculty to automotive engineering and computer science as well. I should say faculty and students. And then my focus area 3, that I'm both a part of and help lead this area. We're looking at virtual engineering and digital prototyping, and looking at the tools around virtual engineering and digital prototyping. So I'll go into a little bit more detail on this. We basically organize this into 5 highly interdependent areas. I won't use the word optimization, but I will use trade space exploration. So as we all know, if you're familiar with sort of optimization techniques, this ability to look at a space, a design space, and it may be a non-continuous design space, multi-dimensional non-continuous design space. How can people visualize that trade space, look at different configurations early on in design, maybe technology infusion, and help make decisions about what the next generation vehicles look like. And there are a variety of techniques in working with folks at GVSC to do this. It's a bit of a challenge, by the way, in sort of the GVSC world or the Department of Defense world. If you're not familiar, they use a term called acquisition, not design. So if we think about sort of the government agencies that manage what the next generation vehicles will look like, they come up with a mission. They determine sort of high level characteristics of what the vehicle fleets need to look like, and then they put those out for contract designers or contractors to design a vehicle to meet those high level missions. And so Department of Defense often talks about acquisition process. They sort of end at scoping the mission of the vehicle, and then you get a number of government contractors that say, yeah, we can deliver a vehicle within that. And then ultimately, they've got to verify and validate that the vehicle solutions meet those needs. So when we're talking about design space exploration, we're typically talking about early stage. A second area of in this is mission definition. If some terms that you may or may not be familiar with, sort of concept of operations or mission profiles. So oftentimes you'll get a bunch of generals or high level folks in a room, an end user of a consumer product, talking about what they want their vehicles or fleets of vehicles to be able to do, how they want them to work together to accomplish a mission. And one of the areas that we're looking at is how do we use some machine learning approaches as well as natural language processing to look at historical missions as well as proposed missions, and begin to move towards more of a model-based approach on these missions. And so we're talking high-level mission requirements, and then working down into some allocated system requirements. We're looking at digital twins and what we're often calling this block here at the bottom, verification and validation. So one of the things that we've come to realize is that we'll use models to predict or help us make decisions about future vehicles. We'll put those vehicles into actual situations and realize that the predicted models, the models that we use to predict the performance may not have been as accurate as we thought they were going to. And so we're looking at using sensor fusion and using field tested data to drive and help us refine those models back. And so we're verifying and refining those models, possibly even creating new models. In the middle, I'll spend some time here in the middle. This is one of the things that got folks at the Army excited. So at Clemson, we have a 2-year vehicle development project as part of the automotive engineering program. So they actually develop full-scale vehicles. To this point, they have developed 12 vehicle platforms where the name of this is Deep Orange. If you do a search, it's called Deep Orange, and the 12th is a high-speed Indy car. 13th and 14th Deep Oranges will be a tracked vehicle, so they are geared more towards the military or Army applications. This development project includes both hardware and software. It's going to be an autonomous vehicle, or the intent is to be an autonomous vehicle. And we're driving both a model-based systems engineering approach as well as some of the virtual aspects. So that is exciting and a little bit frightful as well, because there's a lot of uncertainty with that. Where I sit in this effort of virtual engineering is over here on the basically developing an approach to curate and manage libraries of simulation models or behavioral prediction models. So I guess surprisingly or not surprisingly, this was something that was a challenge when I was a student at Georgia Tech, actually, from 2001 to 2005. So this is not entirely a new problem. But what ends up happening again at GVSC is there's a modeling and simulation group, and it should be pointed out organizationally that modeling and simulation group, which largely sits here, is not the same group that is responsible for mission definition and is not the same group that is responsible for trade space exploration. So from our understanding, those groups do talk, but they're largely responsible for very different aspects of this vehicle acquisition process. What is a challenge is that modelers create models of systems. They create many models of systems. The same system can be looked at from several different viewpoints. And they don't necessarily consider how those models will be used in conjunction with other models, or if they'll be used by other modelers. And you know, the simplest example may be if you've ever created a MATLAB code to do something one semester and you don't put proper comments in it, you don't describe your inputs and outputs, you go back and scratch your head the next time you open it up and try to figure out the logical flow and what the constraints of that maybe small bit of code is, right? And that's a small bit of code, right? So the same challenges that you all probably face and are even responsible for creating those challenges in your PhD studies or research studies are the same problems that the Army sees. Essentially, they have large collections of models. These behavioral models span across many different applications, these simulation tools, and they want to be able to curate those and increase their level of reuse. If you're a cynic, if you're a little bit of a doubter, you want to make sure that people are not misusing those models, right? It's possible to use a physics-based simulation model in the incorrect context. And what we want to do is not eliminate, but make it harder to misuse those models. So what we're looking at doing, again, my specific problem is looking at curating and cataloging those models. It seems to be easy. It turns out it's not. And then developing a retrieval and then a subsequent integration framework to get those models. And the second part, which I'm not going to spend a whole lot on, is how do we compose those models and distribute the execution and the solving of those models within a simulation to help us make informed decisions. Okay, so that's sort of setting the context of this current research. Some things that I would encourage you to think about would be, and maybe we'll come back at the end, what do I mean, or what do you think about when we talk about model fidelity? So when you think about the fidelity of a simulation model, think about what that means to you, and then maybe we'll come back, and if we have some time, we can argue about that at the end. And then think about how you create models. And if you adequately document those models or adequately describe those models such that you can both organize them and then reuse them in the future. All right. So a little bit of context, again, just setting the context of the types of vehicles we're looking at and why this is important. So the first thing is, I think this is important. I think Farouk and Janet, I can speak to them. They spent a number of years and probably continue to spend a number of years looking at product platforms and looking at variety. And if you look here on the left, you'll see a product platform for what's called a family of medium tactical vehicles. These vehicles are still in service. They don't continue to be developed, but you can see the different configurations between them. You can see sort of the 2-axle and the 3-axle configuration. And then you can see the different payloads put on the back of these vehicles. So if you just think about the models that are developed for these vehicles, let's suppose that we create a vehicle dynamics model for the product platform. So this 2.5-ton chassis in the upper left-hand corner, and we're thinking about a mission that vehicle has to go on, and the mission that vehicle has to go on has to go up and over a hill, and maybe do a side hill maneuver. The behavior of that vehicle is very different than the behavior, say, of this 2.5-ton van. The center of gravity has just been raised significantly because of the mass of what's on the back, and suddenly we're managing models that are related to but not the same as for these two different vehicles. And we need to make sure that within that context, within the warfighter's perspective, that we are not putting that warfighter within a situation in which a rollover is more likely. Again, we could think about what this means from autonomous vehicles, so there no longer be warfighters within those vehicles. But managing different models is a big challenge when we're looking at families of vehicles. Another aspect to think about is sort of this recursive relationship of systems and subsystems within a vehicle. So we've had arguments internal to our group that if I'm an engine designer, I'm worried about the individual components of that engine, the pistons, the connecting rods, the cranks, the block, the injectors, all of those things. I may have detailed models of all of those components. So I may have models of all those components at this level. If I am designing the vehicle and the drivetrain, I may only be concerned about what the output power of the engine is. I might be at this middle level. And if I'm the vehicle designer, I may only be concerned about models at this level. And managing these and determining how to plug those models together is a big challenge. I would argue, or we could argue and we could think about fidelity, as I mentioned. Another word, which again was certainly both introduced and got me to think when I was at Georgia Tech and subsequently is abstraction, right? And abstraction and fidelity are not necessarily the same from a modeling perspective. So we're trying to manage models across many of these different levels on many of these different configurations. Let's see if I can come back now, get rid of the annotation. Okay. This is true when looking at these smaller autonomous vehicles. So again, the difference there with the family of medium tactical vehicles is we may have fleets of smaller vehicles. This is a skid-steered system. So this is a track skid-steered system as opposed to articulated steering. This is a wheeled skid-steered system. But we can see how there's different configurations of the same basic unit, whether it be tire models, whether it be different mountings on the top, right? Different sort of features on the top. And then in this case, may be used in different environments. In predicting the performance of this vehicle in different environments with different tires and different payloads becomes quite a complex problem. So I talked about curation and model retrieval. And so what we're pushing is this idea of an ontology. And I don't know who has looked at ontologies or who is engaged with ontologies. Farouk is. I know Farouk, I saw some papers that you've published, and of course we work together. So I don't want this to be a lecture on ontologies, and I don't think we would be able to do that within the time that we have. But I'll go real quickly through what ontologies are, just to set, again, the background on sort of the approach that we're taking. So quickly, and again, we could philosophically argue about what is an ontology, but an ontology really is an explicit description of a domain. And it's an explicit description of a domain of discourse. Okay, so it's something that we're studying and something that we want to be able to represent. And we want to be able to represent that because we want to make sure that there's no confusion, or we want to minimize that level of confusion. All of us on this call could look at a particular domain. Rachel, you must hear my cat. Do you hear my cat in the background or no?
I do, yeah.
All of us could look at a particular domain and come up with a slightly different representation or abstraction of that domain. And it would be maybe because we want to do something different with that domain. An ontology will never address that problem, really. It will never address that problem. So if you think about the domain of a human, I could describe every characteristic about me. If you think about the domain of a human with a phone number, right? That's a different characteristic. And so we want to do things. And so when we talk about an ontology, we have to think about what we want to do with it. So when we talk about an explicit description, we're talking about a computational representation of of a domain that has things, concepts, and I put things in there. These are concepts. Object properties are relationships between concepts. Data properties are attributes about things, and then individuals are specific things. So this is just a really simple example. I've got a concept that is a person and a concept that is a vehicle. Within the concept of vehicles, I am saying that all vehicles are either trucks or cars. We don't have to argue about whether there are other types of vehicles, but are either trucks or cars. And Greg is a individual or a thing within this concept of person. And a VW028 ... is a specific thing in the concept of a vehicle. Greg owns a VW, and that VW is got a data or an attribute about it. That's red. That's got a concept or an attribute of color. I should have put color of here. This is not a complete ontology about the world that we live in. It's an ontology about the ability to ask questions about who owns what vehicles and what color are those vehicles. This does not fully capture all of the relationships that a person may have, does not fully capture all of the attributes that a vehicle may have. But this is an example of an ontology. We typically develop an ontology because we want to share a common understanding and structure and enable reuse. That's why we develop an ontology. We make it explicit. When we make things explicit, we can do things like deploy databases with them. So these could be relational or non-relational databases. They could be knowledge bases. They might be structures for object-oriented programming. And along those lines, we could do software tools or domain apps. So we're typically describing the things, the relationships between things, the attributes of things, and those individuals in order to define, to do something with some purpose. Typically, to develop an ontology, what we'll do is we'll define the terms in a domain. Now, there's an underlying assumption here that that domain is of interest, and that domain has some terms in there. So what we're looking at is defining the terms in a domain, organizing those terms into that domain. I haven't said classes at this point, but organizing those terms, defining the attributes and the properties of those terms, establishing constraints on those properties and attributes, and then ultimately defining individuals and specific values to that. There's not a better way to do this. There's a combination I've seen in both top-down and bottom-up. So top-down might be first principles. Bottom-up may be based on examples or existing sort of formal documents. But this is how one would develop an ontology. Ontologies are living things, meaning they can be evolved over time. Hopefully, we don't see large deltas in the evolution of those ontologies, hopefully. But we can see refinements of those ontologies. We can see additions to those ontologies. They are a curated thing. An ontology in and of itself is a curated thing. They should be released, they should be published, they should be tested, they should be used, and oftentimes within the context of ontologies, there is sort of a larger user group that is able to provide some degree of refinement and feedback to them. A ontology development process. So that was sort of a big picture, a ontology development process. And I presented this because we're going to talk about some of these items moving forward is the following: determine scope, consider reuse, list the terms, which I talked about before. 4, 5, 6 are really about the implementation, if I think. So defining classes, defining properties, defining those constraints. So this is implementation of the ontology. Ultimately creating instances or pushing those instances into that ontology. And I say validate. Now, I would like to point out that there's some iterative feedback here. So we find ourselves in the middle of this right now as we are creating an ontology and attempting to use it. The warning, and if you don't know, or if you're interested, Barry Smith is a researcher at the University of Buffalo. He is sort of an ontologist. I've listened to a number of things from him. Encourage you to go there as well if you think that this could be a useful tool within your research, to support your research. But here are some challenges that Barry Smith says, and I happen to agree with him. There's too many ontologies being built. There's too many ontologies being built. There's oftentimes redundancy between ontologies. And that should be a capital I, but there's inconsistency between those ontologies. So there is, we've seen sort of a large increase in the development of ontologies, probably since the early to mid 1990s. They sort of took off and got increased interest, myself sort of being one of them in the early 2000s. The problem is people build ontologies without determining whether somebody else has already built an ontology within that domain. So you end up reinventing the wheel potentially, or worst case, you end up reinventing an oblong wheel as opposed to a round wheel. That comes from the lack of inconsistency. So here is sort of a way to think about things that I would encourage you guys in this area of sort of knowledge representation to look at. This is a continuum, of course. But I'll sort of walk through this and get you to think about, and I've left one level off. but it's a continuum. So there are things called upper level ontologies or upper ontologies. And some of these are the basic formal ontology, BFO. Another one that I use is UO, which is units of ontology. These are ontologies that have very little terms, very few terms, and they span many domains. Okay, so if you look at BFO, the basic formal ontology does not have that many terms in it. It's certainly less than 30 classes within the basic formal ontology, but it's used by many different domains. It doesn't change a whole lot. It does change, but it doesn't change a lot. The units ontology, units are used by many different areas of science. Doesn't change a whole lot. It's an upper level ontology. So as someone who developed the units ontology, instead of us going forward and reinventing the units ontology, and by the way, it's very complex. The units ontology is a very complex ontology. You have equivalent, so you've got SI units, you have US customary units. There's a relationship between them. There's relationships between pico, nano, micro, kilo. There's relationships there. So the units ontology is actually quite complex. Being able to precisely define that is not a weekend task. It's longer than that. You'll see that the development of this units ontology has taken a while. But you can think about this upper ontology as a language that doesn't change a whole lot. And it should be reused a lot. It should be reused by many other mid-level and lower-level ontologies. So you've got some mid-level ontologies. We actually have some mid-level ontologies that are dedicated to things like the human genome. Okay, this is not looking at maybe how we use the genome for certain aspects, right? Cancer treatment, or maybe the genome is used for other, virus studies, but this is sort of human genome. That would be sort of a mid-level ontology. Within the domain of engineering, there are a few mid-level ontologies. I've called one of them out. This is the Common Core ontologies. It defines things like artifacts and parts of artifacts and events and processes. This Common Core ontology imports or uses terminology from the upper ontologies. And then we can move down here to the lower level ontology. So there are several lower level ontologies. There, show you some examples. These are domain specific ontologies that, again, leverage and import or specialize some of the higher level terms. And the one level that I've left off are things like machine ontologies or software ontologies, which is very specific to a particular implementation. If you're interested, there's a couple of different efforts. There's actually what they call a Industrial Ontology Foundry, managed as a working group, I believe, at NIST. It's a fairly new working group. So if you think about this, we're in 2020. I talked about sort of the increase in ontology interest dating back to the 90s from efforts at Stanford. 30 years later, we're finally realizing that the growth of ontologies and the entropy with the developed ontologies is not something that is desirable or productive. And so there's an effort to help guide that. So just again, a couple of slides here, which I think are of interest to you. This is a list of the mid-level ontologies that use the basic formal ontology. And so what you'll see here is the names get longer and the applications get a little bit more specific, which sort of goes in line with the purpose of these ontologies. And then here is actually quite a nice thing, and also a bit of an alarming thing. I mentioned the units ontology. So this is BioPortal. Ontology development has seen tremendous usage within the area of bioinformatics. And within this, there are at least 3 different ontologies used for units of measurement. Ontology of units of measure. This was just uploaded, by the way. Units of measure ontology, updated in the end of 2020. And then units ontology would be, well, look at that, 9 years old now, 10 years old. So sometimes people don't use, we talked about sort of the redundancy of ontologies. It's, you'd have to do a little bit more investigating. This ontology of units of measure could quite possibly be a specialization of some of these units, but you can see here within this bio portal the different ontologies that are available. And then again, just to sort of get a few more points across, this is an example of the ontologies within the Common Core ontology. It uses terms from the basic formal ontology. This is great, BFO. And it specializes those according to things like artifact ontologies. We'll talk quality ontologies, units of measure ontology is an import, time, and this creates a mid-level ontology which has been used for, and these I've only included 7, has been used for a variety of other lower level or domain specific applications, aircraft, military, sensors. And so these ontologies use terms here and then specialize them a little bit more. Okay. Any questions so far? All right.
And
hearing none, I'll move forward. So, yeah.
If anyone has any question, you can put in the chat box as well. I can Greg can answer.
Yeah. So, what we were struck with is this massive amount of simulation models. And these simulation models that are used across different modelers. And what we came to the realization of, and we weren't trying to use a tool, that being ontology, to solve a problem. It's actually quite funny. Last couple of years, I was feeling a little bit guilty. I had this great skill set that I developed as a PhD researcher at Georgia Tech, I think, in the area of ontologies. And I've taught some courses here at Clemson in the area of engineering informatics, which this becomes a major thing. And as I looked at sort of my research portfolio, I said to myself, well, holy cow, I haven't used that in a long time. I haven't gone back and looked at formal representations. I deviated into things like creativity and early stage creativity, looked at the sort of distributed design and manufacturing, teaming and student engagement. But I had this tool in my back pocket, and I hadn't looked at it in a long time. As a matter of fact, the last time I think I looked at it, Farouk had a student, a PhD researcher, looking at ontological development of decision support problems. And I had a conversation with that student, I think back when I visited you in 2017, but also maybe at an ASME conference. And I thought to myself, man, Greg, you're not using this tool that I have. So I didn't shoehorn sort of a skill set that I had into this problem. I had done some things to get myself prepared, I think, for this opportunity. So that might be something that you can think about as you're on your PhD journeys. The things that you do will prepare you for potential opportunities in the future. So when you get an opportunity to sort of put something in your quiver and in your toolbox, you may not use it immediately, but it may prepare you for opportunities in the future. So that's Mocko's musings. All right, so what we're looking at, we said was we think that if we develop an ontology, if we look towards sort of ontology engineering, we think honestly that we can solve some of the problems with what GDSC is having. We think that we can help them curate and organize their They're models. We think that. We think that we can do that, but hold on a minute. Some other folks have done it, and it doesn't seem to have sort of been embraced as much as we think it should be. There's been some other ontologies developed and actually supported at GVSC. If you go back to the development of the Common Core ontology, that's actually been funded and supported by Department of Defense efforts, to be honest with you. If you look at some of those ontologies, there's a spacecraft, there's an airplane ontology. I'll tell you, in my experience with UAVs, the use of simulation models are there as well. The subsystem breakdown is there as well. It's slightly different than a ground vehicle, but certainly not polar opposite. And so we as a research group here at Clemson have to figure out why folks are not using these ontologies that have been developed. And I've got some hunches why they're not using them, but maybe it's fundamentally incorrect. Maybe they didn't go about a good methodology. There's another sort of more superficial perspective, and that is when you start to look at these ontologies, we have to think about tools that use them. The ontology is not the end. Tools that use them to make an engineering designer's life easier are sort of the end. So what I want to do is go over a few steps, and I should point out what I'll talk about here is presenting the methodology, and I'll walk you through the first few steps, looking at the domain knowledge, and then talk about sort of the next step. So we are in the midst of this this project. As I said, we're about 10 months into it. So I want to talk about what we're doing to work towards the development of an ontology. So go back to this process, talk about the first 3.5 steps in this process. The first 3.5 steps. And the first 3.5 steps really set us on the correct direction to hopefully create something that GVSC can use. So the first thing in developing an ontology, I said, is determining scope. So when determining scope, we're looking at autonomous ground vehicles. We're not looking at air vehicles at this point. We're not looking at water-based vehicles. We're looking at ground vehicles. We're looking at the early stages of the acquisition process. We're interested in predicting and modeling the behaviors of these vehicles. We're looking at the inclusion of a vehicle, the driver, passenger, and the environment. This is important. This begins to set the scope. We're looking at different software applications. We're looking at models of varying fidelity. So there's that word that I've encouraged you to look at. And then we're looking at different models. So we're defining our scope here. Like, we need to make sure that we understand the scope of our ontology. I haven't gone into great level of detail here. We've got documentation on a bit more about the scope and what is not within the scope. But a challenge that you'll probably find if you participate in a design project is very easy for scope to creep. And when that scope creeps, it's very easy for a solution that you think have to your scope suddenly becomes not a useful solution. So what we want to make sure when we're talking to researchers within our center, as well as within the associates at the Ground Vehicle Systems Center, that they understand what scope we're looking at. It should be pointed out that we have come up with this scope by communicating with engineers and modelers and scientists in the other two focus areas. So we want to determine scope. So what we're also looking at is the scope comes from examples of models that we have. So we're looking at all of these existing models. We're looking at how these models are used within the vehicle development process. And we're looking at current best practices of vehicle architectures and models. So I want to present a couple of examples here in determining scope. It should be pointed out that these are examples. These are fairly new examples. They are not ontologies at this point. So two examples that I'll call out to you, which I think are interesting. This is a architecture of a ground vehicle system. It's published by SAE. It's an SAE standard, released in 2017. It goes into a lot of detail. So it's several hundred pages. I haven't gone here, but basically what this defines is the following. It says, at a high level, a ground vehicle system consists of an environment, a vehicle, and the drivers or passengers. Again, there are several subsystems to this, which I'll talk about a little bit. And these high-level systems that compose together and make up a ground vehicle system are actually connected together with these flows. So this is our baseline architecture. We're saying that after several years of experience, several different people, experts in the area, have determined that these three major systems are connected together with these flows. And this is sort of a best practice. This is sort of a best practice for the physical systems, logical systems, as well as the connections between those systems. Okay. Second best practice we've looked at is a recommendation from SAE on how would somebody document their simulation models in the area of and domain of ground vehicles. So we've looked at this. We've talked to researchers at Ford. We've talked to researchers at GSC. Just to point this out, there's about 130 different fields that a modeler would be required to populate in order to accurately document their model. It's a lot of fields. It's not used. It turns out this is not used because of that. And talking with our colleagues at Ford, they feel that there's just too many fields. And when the documentation process is too much of an effort, what happens? Nobody documents. And it's easy to not put comments in your MATLAB code. But we're using these as sort of the scope. We're looking at scope. So the other part of scope, I told you early on, and I see a question here. So the other aspect is in determining scope, you have to figure out what you want to do with the model. Okay, so I'll give you a simple example. I don't go to the phone book, which is a database and has an ontology underlying it, to find out medical records. The phone book is a fine model, is a fine database. It just turns out it was never intended to query and find medical records. It is an ontology. It is a database for a purpose. So in addition to scope, you need to figure out what sort of questions you want to ask of your model. And some of the questions that we asked or are wanting to ask is, how do we retrieve models? How can we find models that are a particular subsystem? Can I find different models for different engines? Can I find different models for different tires? Can I find different models for different soils? How can I find chains of models? So if models have been plugged together, so one model is connected to another, model is connected to another model into a larger simulation, can I find where those models are able to be plugged together or linked together or have been linked together? Can I organize models on phenomenon if I'm looking at an underlying physical phenomenon? Some of you guys have talked about, I think, carbon capture. What sort of phenomenons and different phenomenons are used in carbon capture? Could I look at how those different models are used within a particular simulation, a larger scale simulation? And again, here comes this word fidelity again. Can I look at models based on different fidelities? So a question that we have philosophically is, if I've got and I'll use these two terms, and if I have a low fidelity model and a high fidelity model, is that good or bad? So I've got one that is very high fidelity, and I've coupled that together with a very low fidelity model. What are some of the positives and negatives of doing it? What are some of the shortcomings and what are some of the alarms that I need to know as a as a designer about what to do with those high fidelity and low fidelity models. All right, so what we're looking at now is sort of jumping ahead. We've defined scope. We're thinking about, all right, what are we going to do for reuse? So I've organized this into two separate ontologies. Okay, I've got the ground vehicle architecture ontology, and I've got a simulation model ontology. And now I'm beginning to look on the industrial ontology foundry for existing ontologies, things like BFO, the units of ontology, and the common core ontology to reuse these items. Now, I have separated these two items out, simulation model ontology and ground vehicle architecture ontology, because I think that I may be able to replace this with UAVs, for example. And what will change is the structure of the UAV, but the underlying ontology to represent simulation models, we don't think will change. We think that simulation models can be described in a uniform manner regardless of the domain or discipline that they're used in. That's our goal. So when we're thinking about reuse, we're thinking about, I'm going to reuse these ontologies here, and I want to create a simulated ontology that allows me to formally model and understand aspects of both ground vehicles and simulation models. So reuse, I'm looking, well, I say I should point out that, and we'll get to this at the end, it's not just me here. But we're looking at the units ontology, right? We're looking at an ontology called quality. Quality is a way for defining things like, I've got a value, that value has a unit. Relationship ontology, so common core ontology has defined relationships which you and I will take for granted, like part of relationship or subsystem of relationship. And then there is another integrated ontology, this QUDT, which actually integrates qualities, units, dates, and times. QUDT is an integrated ontology. This should have an S on it. I apologize. And it turns out, as we look at these, how are these new ontologies developed, and are there new ontologies? So we're considering reuse. As I pointed out, we do not, as a group, want to develop new ontologies. We don't want to develop our own ontologies. We don't want to make mistakes. We want to leverage these. Now, here is something to consider when using an ontology. If this units ontology, and I'm not saying it is, if this units ontology is poorly curated, meaning there's fundamental flaws and mistakes within it, and I happen to use it, I have just used or imported their flaws and mistakes. So if you look at that industrial ontology foundry, there is actually a process in order to get your ontologies validated and made available for public use. Right? We want to make sure that there's not, somebody hasn't determined that there's 5,712 feet in a mile, right? That's a bad thing. So we want to make sure that those ontologies are validated. Want to list the terms. So what we're currently doing is extracting out of these different standards, and we're looking at ground vehicle systems and simulation models. And I'll just show you a couple snippets of this. So we've gone through and listed these terms out. And they come out of a variety of sources, a variety of special interest groups focused on modeling and simulation. So you see, again, for accuracy, for example, slightly different interpretation of accuracy. Abstractions got different interpretation or different meanings. I'll give you just a couple of snippets. So we're extracting out what is a simulation. Okay. So simulation is an important thing. We're developing a simulation model ontology. We should probably have a good definition of what a simulation is. What is a model? What is a model interface? So again, within our group, our research group, it's going to sound crazy. We argue about what a model is. We've argued the last couple of weeks on a model versus a model fragment. So some of us think a model fragment is a model of something that you can't use unless it's plugged in with another one. The problem is we run into a recursive relationship. So if I develop a model of a transmission, yes, a transmission is not the only component on a vehicle, but it is a complete model. It can be executed, right? I may need, for it to make sense, I mean, it may need to plug it together with an engine model and a drive shaft model and a rear end model and a tire model. But this idea of what is a model versus a model fragment, model interface. So these are the terms we're collecting, and a few other things like variables and parameters. So what is a variable and what is a parameter? It should be noted that a quality can either be a variable or a parameter, depending on what our model captures. And then we're currently extracting out all of this information from this, this diagram that I showed you earlier, and we're working to implement a glossary like we had, and then that will serve as the list of terms for our ground vehicle architectures. So I jumped over that. So what we're currently doing now is we're taking this glossary out, and we're not presenting all the terms to all the researchers. We have an idea on what terms are important, and we're attempting to look at existing tools that are used by GVSC and our researchers in our center. So for example, there's several researchers using MATLAB Simulink to create models of batteries and motors. And we're working with them to see if our terminology maps to their models, and we're able to document it. And if their models, if they can document their models using our terminology. If you haven't looked at it, there's a really great multi-physics engine called Project Kronos. It's freely available, developed by the University of Wisconsin. It's used for many different multi-body dynamics problems, and would encourage you to look at that. So what we're currently doing is taking our terms and cross-checking those terms to make sure that we indeed have got no confusion of terms, as well as a full coverage of terms within our center and GVSC. I'll talk a little about this. We're working towards defining classes. I'll show you a few snippets here. Please keep in mind that these are drafts at this point. We've got a couple of things going on as we do this. One is training some researchers to use some software to author and create ontologies. And then the other is to begin to put some order to our terminology. So we feel pretty good about these first three steps. And now we're going to begin to implement the ontology. So what we're currently using, and I see some questions here, and I'll try to answer them, is we're using the OWL language, which is the web ontology language. It's a standard sort of XML RDF implementation that allows us to capture ontologies in a computer interpretable format. And again, I think Farouk waved his hand. He's probably used OWL on his ontologies, and we're using Protege 5.5, and this would be the tool that was developed at Stanford within their medical informatics group for authoring ontologies, and is really quite a nice sort of. It's not a programming tool, but it's a tool that allows you to create and author ontologies. And then we're looking at some languages, so two query languages, Swirl and Squirrel. These two languages allow us to actually query ontologies and do some reasoning within ontologies. And then we're using GraphFoo, which is really an ontology, visual ontology language or tool. So I'll show you a few examples here. This is actually a GraphFoo representation. So we've taken those terms. We've taken those terms and the relationships between terms, and we have created a formal explicit, so that's an ontology, a formal explicit representation of a simulation model. I'm not going to go through all of the details here, but I'll cover a couple of them. This is not complete. This is This is what we currently have. So what we're basically saying here, if you read this, is a model has a title. Okay, that's great. A model is created by a person and uses. So a person creates a model and a person might use a model. Those might be different. Those might be different. A model has both variables. If you remember correctly, those variables change during the execution of a model, and has parameters. Those might be qualities that don't change during the execution of a model. This is a pretty interesting aspect about an ontology. So if you'll look here, both of these object properties point to quality, okay? But when we relate them in different ways, they take on a different semantic meaning. Okay, so we don't have two different classes that say variable and parameter. We're saying there's one class that is a quality, and that class in the context of a model can either be a parameter or a variable. So a simple example, maybe you have a simply supported beam, and in one model you're using the Young's modulus of that beam as a parameter. It doesn't change. And in another model, you're using that quality of Young's modulus as a parameter that changes within the context of that model. Again, that quality has a unit. That quality may also have a type. So it might be a continuous type of quality. It may be a discrete type of quality. And then we've got some descriptions to what these are. Something over here, what you'll see is these are object relationships between things. They have some semantic value. This is a subclass. So we can say a type. It doesn't have a type. This is a subclass. This is a class. That's a different type of relationship between things. I won't spend a whole lot of time in here, but this is a relationship that represents our highest level architecture. So we're saying a ground vehicle system has a subsystem of an environment, has a subsystem of a driver passenger, has a subsystem of a vehicle. This vehicle has these subparts. Again, this is not, for the interest of presentation, I did not include all these parts, but this is an ontology that comes from the terminology that we spoke about. And then here's a slightly more detailed representation of this. This is in a visualization tool directly. So I won't go over this, but let me jump ahead here and say the following. So where we currently are at, I talked about developing a simulation ontology for ground vehicles. So we're looking at the simulation model ontology, and I have these flipped. How about that? The simulation model ontology is here. Ground vehicle ontology is here. We're combining these together, and we're actually going to use them to create this model library. Okay, so we're gonna populate this with instances. So what you won't see here is the instances that we have, but we can think about specific models that have specific variables. And then we can leverage, this is not a database per se. We can leverage some actually intelligent aspects, some mathematical aspects about ontologies that infer things like subclasses and subtypes, which are really quite powerful. So what we're currently doing is gathering some models and working with our researchers in the other areas. And then longer term, what we'll do, I say longer term, in about the next 3 months, what we'll do is actually create a library of models to be used by students in the Deep Orange project to help them actually make informed decisions. And with that, I will be happy to answer any additional questions